Okay, thank you so much, guys, for coming today. We're doing our review for Midterm 3, and I have it on Tuesday next week, so you get the weekend to study. So lectures 11 to 15. I hope you brought your packets with you. Did you? Good. All right. So we'll start off with the neurons and glial cells. As usual, I'll talk about the exam format, which you should be used to by now. It's going to be very similar to what we've had before. Our section 1, of course, is the multiple choice, right? And you have 30 times 1, not 20, which is 30 points. And then section 2, the usual short answer questions, all right? And that's going to be 5 of 6 times 2 equals 10. And then section 3, it's going to be long answers as usual. It's 4 of 5 times 5, 20, 30, 60. Okay, so it's the same format we'll be doing. So we start off with the neurons and glial cells. Neuroglial cells is the full name for it. So, of course, you've got to know about the functions of each system, right? Okay, so the central nervous system receives sensory input, right, from all the body parts, and gauges the internal environment. Then it will send out messages to either glands or muscles to perform an activity that maintains homeostasis, right? So when you talk about those functions, you have to kind of sort of flesh it up a little bit and talk about what that function involves for each system we talk about. And then, of course, the control center, right? The brain has all the set values for all the points. For instance, temperature. It knows that temperature has to be 37 degrees C. Okay, so if it goes out of that, range, then it'll send messages to either glands or muscles or whatever needs to do the action to perform action to maintain homeostasis, which is maintaining a stable internal environment, right? So that's what the nervous system does. It's the major control system, and it tries to maintain a stable internal environment. So gotta know all those functions of this. Of course, this is like a 5-point question. And of course, mental activities. All right, that's where you have your thoughts, your memory, and so forth. Decision making, all that is the nervous system, right? So gotta know that. Always have to know the functions of each system we talk about, right? So gotta know how it's organized. Okay, this is one of the questions I asked, how the nervous system is organized, starting with the central nervous system, which includes what and what? Yeah, I was going to finish before you told me, you know what I'm saying? I was writing faster than you guys were saying. Okay, so that's that. And then the peripheral nervous system would be the, what's the peripheral nervous system made up of? 2 things, quickly. Cranial nerves and spinal nerves. Yes, thank you. Cranial nerves, spinal nerves, right? So you gotta know each. Sometimes I'll say, how is the nervous system organized? Can you tell me the divisions and subdivisions of the nervous system and what their components are? Then you talk about this. Okay, that's a very good question. And this is the one, the sensory is the one that takes all the sensory information, takes it to the, remember the sensory function we just talked about? Okay, so it is towards the CNS, right? It collects from the periphery. Okay, it is the motor division that's divided into the somatic, which deals with muscles, and the autonomic, right? Which deals with all those things that are automatically controlled, like the name suggests, right? So this will be muscles. Okay, so you need to know that, and of course, so this will include things like the heart, viscera, meaning digestive organs and so forth, all the smooth muscles, okay? blood vessels. All those have smooth muscle that is controlled by the autonomic nervous system. All right? And the autonomic nervous system is split into these three. What does the parasympathetic usually do? Inhibits or stimulates? Real quick? Okay, inhibits. You should kind of know these guys. Sympathetic, of course, does the opposite of that, which is to stimulate, right? The sympathetic, if you're sympathetic to somebody, you kind of want to aid to them. You kind of want to stimulate them, okay? So that's how you can kind of sort of tell them apart. Parasympathetic, then it inhibits. Okay, stimulates. Okay, so not only do you have to know this, so what does the enteric do? What does the enteric, what is it involved in? Which system? Digestive. Okay, very good. Okay, so you talk about that. So this is the basic organization of the nervous system, so you gotta know that, all right? And then, of course, we got two cell types in the nervous system, right? Neurons, which we said are the excitable tissues, okay? And they can send messages via the axons, okay? And then the neuroglia, or glial cells for short, which we say support and nourish all these neurons, right? Very important, right? Because neurons don't do what? They don't regenerate, so they need a lot of support and to have all the machinery to, create spare parts, if you will. Like for instance, if a dendrite falls off, you have to create proteins and so forth to repair it. So what do neurons have for that ability? What we call it starts with an N. It's a special, organelle that the neurons have. Well, yeah, but this one is to do with the producing material for repair. What organ produces material for repair in a normal cell, anyway? Huh? Which organelle does that? In a normal cell, rapidoplasmic reticulum, right? Okay, does protein synthesis. Okay, you should know this, guys, because this was in. So those are the characteristics I'm talking about. It doesn't regenerate. It is what are called Niesel bodies. Okay, Niesel bodies are, accumulations of rapidoplasmic reticulum and a lot of ribosomes, where protein synthesis occurs. Okay, so those are the characteristics I want you to tell me about. What else about the neurons? They don't have centrioles, right? That's why they cannot divide. Okay, all those things I need you to know about that. All those characteristics, centrioles, and so forth. Okay, don't regenerate. Sometimes I may say, oh, what are the neurons of the? What are the functions of neurons? What are the characteristics of neurons? Okay. And, so and so forth and so forth. So it sends, receives messages, right? Messages. It sends and receives messages. All right. So you gotta know all about that. All right. And we got the types of neurons as well. Okay. There's three types: multipolar. Okay. There's more than this, of course. I'm just trying to be fast, right? And then, so you should know the characteristics of it as well. This part that generates the impulse is called the, starts with an H. It's called the hillock, right? Axon hillock. All those things. Or the trigger zone. Remember the trigger zone? Yes. And then, so this is the cell body. You need to know the parts of it, the major parts of a neuron. It's got, what is this? These short processes. Dendrites. Okay, and this is the axon. Okay, and this is an example of a, what type of neuron is this? The one I just drew. Multipolar, okay? Then there's other ones. That's an example of a bipolar disorder. Because it's got 1, 2 processes, right? Now this one is unipolar, right? So gotta know all those, types of neurons. Sometimes I might say, can you, name 3 types of neurons and describe them, and give me a function for each. What would be a function for the multipolar? For like integration, right? It's the one that's mostly in the nervous system. And motor neurons, control of muscles. All motor neurons are multipolar, okay? What about the bipolar and unipolar? What did we say they are reserved for? What are they reserved for? Huh? Somebody said it. Quick. All the things on my face. Special senses, yes, like sight, hearing, and all those things, okay? Smell, all those special senses, okay, guys? Because I might just ask about that, you know what I'm saying? 3 points. You get to what, 2 points and then a bonus. Name them and describe, you know, the types of neurons and give me functions. Okay, I'll do that. Don't say anything. Okay. Okay, so now we go to these ones, which is the bulk of these brains, the neuroglia cells, for supporting and for anchoring all these neurons to nutrients like blood vessels, right? Okay, so we get 4 in the central nervous system and then 2 in the peripheral nervous system of these neuroglial cells, okay, or glial cells, okay? Astrocytes, we said they are star-shaped, and we said they do what now? What do they do? All those, because sometimes I might say, oh, can you give me the functions of astrocytes? Remember, they produce the blood-brain barrier, okay? Mop excess ions, okay? Mop excess ions, you know, like clean up after you have all these action potentials going through with ions going into and out of the membrane. They clean up, all right? They do repair, okay? They repair, so you gotta look up those notes and gotta know these functions and the general characteristics of each of these glial cells. And sometimes the name will tell you too, the characteristics right there, except for this one, okay? The pendulum doesn't show you anything, okay? But it produces what? What fluid in the brain? Cerebrospinal fluid, and it's got ciliated cells, you know, cells that have epithelia that line it is like that, and then it's got cilia to move and circulate the cerebrospinal fluid within the ventricles, okay? So it lines special blood vessels called choroid plexus that are suspended inside the ventricles of the brain, okay? And so forth. So produce cerebrospinal fluid and maintain ion content and so forth, because the nervous system conducts action potentials, and we all know what action potentials involve: movement of ions across the membrane. So cerebrospinal fluid provide all those special ions, sodium, potassium, things like that. Okay? And then neuroglia, we said they are the small. Yeah, they are small. They're very good. You see, the name tells you. They're small, and they are the what function do they have in the brain? It's an immune system function. So these are the macrophages of the brain. Okay, they engulf any bacteria and so forth. They protect the brain. Engulf, and then oligodendrocytes. We said it's few dendrites. Okay, and what does it do? Do you know, anybody remember what this one does? Produces what? Myonin, right? Sheath. Okay? All right, very good. So Schwann cells do the same job in the periphery. They produce the myelin sheath. Okay? And then satellite cells, they support and so forth, cell bodies. Satellite cells, they surround ganglia, right? Remember, ganglia are cell bodies in the peripheral nervous system, right? Ganglia are cell bodies in the peripheral nervous system, whereas nuclei are cell bodies in the central nervous system, okay? So they surround ganglia, okay? Surround, okay? Surround, okay? Very good. So gotta know these cells. Sometimes they'll ask about one of those cells. It's like, okay, you tell me these cells, you know, these glial cells in the central nervous system. So you've got to know which ones belong to which, and you know what they do to which part of the central of the nervous system. So those cells we just talked about, the glial cells, Schwann cells, and so forth, and and oligodendrocytes, they create the myelin sheath, which then surrounds the axons, right? It's only the axon that can be myelinated, not the dendrites, okay, not the cell body. Only axons can be myelinated, and it's like an insulation. That part that is surrounded is insulated, and it's got fatty acids and lipoproteins, and it's whitish in color, and it's what creates the gray matter, okay? And then the spaces between the myelin sheath is what is called the nodes of Ranvier, okay? So what's the function of the myelin sheath? One I said it already is to insulate. What's the other one? Yeah, to speed up the action potential, okay? Speed up action potential and so forth. All right, so that's that. And then unmyelinated axons, they don't have the myelin sheath, but they are still surrounded by the Schwann cells in the periphery and the oligodendrocytes in there. To do what? To insulate, right? Because they still need to be insulated. They're sending signal too, electric signals, okay? And so they don't have the myelin sheath, and they conduct slower action potentials, right? Compared to the other one, okay? So organization, the myelination causes the formation of white matter. Anything that's myelinated appears whitish, and all the structures that are not, like the cell bodies and so forth, cell bodies, what else? Dendrites, and what else? And some axons, because not all axons are myelinated, right? All those structures create the gray matter, okay? So I asked you to describe it in the exam, okay? So, so we move on to number 2. Since we just talked about the nervous system, which does all these sending action potentials and so forth, okay? So we go to action potentials, number 2. Okay, so action potentials are electric signals. They are minute electric currents that the body uses to communicate. Okay, so that's what. So an action potential, spreads across the axons of the membrane, and it has to reach threshold first. So it sends impulses on axons, right? And that's how the neurons communicate within themselves and also with other tissues like muscles and glands. Okay? So, what is the source of these, electric properties of cells, right? It's of course the ion concentrations on the inside and outside of the membrane. Okay? So that's what allows the membrane to pass an electric current. Okay? And then not only do you have certain cells, certain ions outside and other ions inside, you have to have some gates, some channels that will let those different ions in and out. Okay? So depending on what ions it has, that's what channels, then it will determine the electrical activity of that cell, right? So the permeability to these ions. Which channels does it have? What ions can pass through? Okay. Okay. So how do you create the gradient? So like a separation of the charges, so that you certain charged particles on one side and certain particles on the other. So what creates that gradient? Okay, is the sodium-potassium pump, which pumps 3 sodiums outside and 2 potassiums inside, right? So then you have a differential in the number and type of ions on the inside and the outside, right? That's how you create the electric signal, okay? So you can have an electric signal because of the concentrations of ions and because of the membrane permeability, okay? And then you need a gradient. So there are 2 things, okay? Not only do you need the ions and the permeability, you need also to create a gradient, a difference in the number of electrons. So you get that and that. The ion channels now, some are leak channels. Leak channels are always open, right? Okay? And the cell happens to have more potassium leak channels. So potassium tends to leak out a little bit more than does sodium. So it kind of creates a more positive charge on our side because potassium, after all, is positively charged. Okay, and then there are gated ion channels. And there's like two types. We've got the ligand gated, that something attaches to it and it opens. Then we've got the voltage gated, which are the ones that really work for these action potentials. Is a change in the voltage and then it opens. Okay, so that's what creates the gradient. Okay, so be careful if I ask about the sources of the electric current or why it's able to do that, and also how you're able to create the gradient. That's a different story, but it's also related. So these are the ions we just talked about. Ligand gated, something attaches, voltage gated, changes in voltage, and then other, gated channels like say mechanically gated, like touch, something that's mechanical, it touches it, these are more for the senses, like mechanical gated. Like touch receptors are mechanical gated. They, tactile stimulation creates a current. But for action potentials, we are mostly interested in those. All right. So, resting membrane potential. Okay. The definition of it, it's it's the membrane potential of a cell when it's not doing anything, when it's not being stimulated, right? It's the membrane potential when it's not being stimulated, and then the characteristics of it, there's many, okay? And I gave you a little table, right? Resting membrane potential is minus 70 millivolts for starters, right? If you start from there, you realize that in the inside, it's more negative. That's a characteristic of a resting membrane potential. And the outside is more positive, all right? And then you can also say the outside is more sodium ions, okay? More sodium ions. The inside is more potassium ions, okay? And then you can talk about how the negatively charged ions are too big and they don't have channels to exit. So the negatively charged ions stay inside the cell, which means that the inside is more negative. That's why it's minus 70 millivolts, okay? So you talk about all that. There's a table that I showed you with many of these characteristics, okay? You need to know the conditions at rest before you can talk about an action potential. You need to know where you're starting, okay? So to know where you're going. Okay, so when you change the membrane potential, you can do two things, okay? The membrane potential is like this, you know what I'm saying? This is 0, this is minus 70. It's like that. So you could depolarize it by going, opening sodium gates. That means it's becoming more positive. And then usually gradient potential fades away like that slowly. Or you could hyperpolarize it, okay, which also fades away slowly like that. So this is depolarization, this is hyperpolarization. It means you are going further from minus 70, okay? So those are the way you can change. You can either go up or down. It's only two things, okay? So if I ask you to describe how to change how the membrane potential can change, you can describe the depolarization, becoming more positive, or the hyperpolarization. Those are the only two things, okay? So gradient potentials, what is the definition of that? These are small action potentials. I mean, not action potential. That's not good. No. Don't say small action potentials, because an action potential is big already. So these are, small membrane potentials. Okay, that are usually, are conducted in decremental fashion. Okay, just like this. You see, this is a small membrane potential, and then it fades away. Okay. Sub-threshold membrane potentials, okay? Because if it reaches threshold, what happens? Action potential happens. So anything that is sub-threshold is a gradient potential, okay? So sub-threshold. Because if let's say threshold is there minus 55, right? And it goes up to here, or it goes up to minus 60, still nothing happens. It will just disappear. So a gradient potential, any membrane potential that is sub-threshold, that is under threshold, okay? So you gotta, and then the characteristics, of course, it is conducted in a decremental fashion, and then it disappears, okay? And it could either depolarize or it could hyperpolarize the membrane, all right? Okay, so gotta know that, the characteristics, okay? And the types, of course, depolarizing, and hyperpolarizing. All right, so very good. All right, so gotta know those. And then, of course, action potential definition. These are large membrane potentials that reach threshold and are propagated along the axon. Okay? It will go to maximum depolarization and then come back down again. And then when that happens, it generates a current that stimulates the next part of a membrane. So an action potential is propagated along an axon. Okay? So these are large action membrane potentials that reach threshold and are conducted along the length of an axon. Okay? And then it's got 3 phases, right? An action potential has got 3 phases. Okay? So this is resting membrane potential, and then we have a depolarizing action potential. It reaches threshold, boom, boom, and then it always goes to a certain, for each tissue, it never goes more than whatever the value is. In this case, I'm using 30 as an example. Okay, so each tissue has a certain size action potential that always stays like that. It doesn't change. Okay, and then of course depolarization, and then okay. So here you should know that in the exam, draw yourself this little graph and say what's going on. Okay, Na plus in, and this is deep polarization, and then here you can say K plus out, and then this is repolarization, and then because this is happening extremely fast, it will pass resting potential and kind of dip down. That's what's called after potential or after hyperpolarization. Okay, because it will dip down and then it will come back to resting, and the sodium potassium pump will re-establish the resting conditions where you once again have sodium outside, potassium inside. Okay, so be able to describe these phases of an action potential and be able to show me what's happening. Like depolarization, you say sodium gates open up and then sodium rushes into the cell. Because you know that sodium at rest is on the outside, right? It will flow down concentration gradient. Okay? And then, of course, repolarization, sodium gates close, potassium gates open, and potassium rushes out because it's more inside, okay? And then after hyperpolarization, it will dip down below, the resting potential and then come back again, okay? And then there are refractory periods, 2 types. One is absolute refractory period, okay? So which is pretty much from depolarization all the way to hyperpolarization. It's absolute refractory period. While it's going through an action potential, that part of the membrane will not be stimulated ever. It doesn't matter how strong the stimulus is. Okay? But from there to there, relative refractory period, kind of whenever you get a strong action potential, stronger than threshold, you could have an action potential. Okay, so the absolute refractory period ensures that the action potential only goes in one direction, right? Because when an action potential happens, it will send a current forward, it will send a current backwards. The electric current will just be generated around it. And because this part of the membrane going through is under absolute refractory period, it's not going to be stimulated by this current. It's only going to stimulate the part in front of the action potential. So that's how the action potential is propagated in one direction. Okay? If I ask you to explain how an action potential is propagated in one direction, can you do that? Like as a bonus point? And I'll say, how is the action potential only propagated in one direction? Then you talk about the absolute refractory period. And you say that part that the action potential is going through is under absolute and it cannot be stimulated. So it can only stimulate the parts of the membrane in the front that are not. Okay? So that's how it goes in one direction. All right. So action potential frequency. All right. Because remember I told you each tissue has got the same size action potential. It doesn't change. So how do you know the difference between strong and weak stimuli? Is the frequency. Okay? So the number of action potentials you are generating per unit time. That's how strong it is. If I generate 3 action potentials in a second, Yeah, that's okay. That's not too bad. If I generate 15 action potentials in 1 second, that's a very strong signal, right? Okay, so that's that. So sub-threshold is going to be a graded potential, right? Because it's not going to do anything. It's going to be under threshold, so it's just going to disappear, okay? Because it's actually generated in a decremental fashion. It depolarizes or it hyperpolarizes, then it sort of gradually comes back to zero, to resting, okay? So that's that. And then sub-maximum is above threshold, but not quite maximum. So this you get an action potential, right? Okay? So you get one action potential here. If you have a maximum or supramaximum stimulus, then you get a whole bunch of these action potentials. So the frequency goes up per unit time. Okay? So that's a strong signal. Okay? That's the only way the nervous system can tell the difference between these signals. The frequency, the number produced per unit time, and so the stimulus, the strength of the stimulus is proportional to the membrane potential change. Okay, that's what graded means. Anyway. Graded means the size of the stimulus, okay, or the size of the membrane potential change is directly proportional to the stimulus or the size of the stimulus. Okay. All right, so. Propagation of action potentials, we kind of talked about it a little bit. We said that they're only generated in one direction. Okay, like the band, one direction. You're kind of slow there, you didn't pick up on that. Gotcha. Okay, so because of the absolute refractory period, it's generated in one direction, and then the myelination causes it to be much faster. Because myelination causes saltatory conduction, right? Where it will jump through the nodes of Ranvier only, because the nodes of Ranvier are the ones that are not myelinated, right? The other parts that are myelinated are insulated, so action potential can pass through there. So it will jump, it kind of shortens the axon. Okay, so that's how it speeds up. Okay, the action potential conduction. 3, synapse. Now we're talking, we're kind of sort of moving on in kind of incremental fashion here, right? Now we talk about synapse. We talked about how you conduct the message. Now we're talking about how it's passed on to the next tissue, whether it be muscle or it be another neuron. Okay, so we talk about synapse. Okay, synapse is, what did we call it? It's a functional connection between two neurons or neuron and other tissues like muscles and glands and so forth. Okay, so it's functional. It's not physical because they don't touch. Okay. So it's functional connection. Connection, that's my shortcut for connection right there. Okay, so, and we said we get 2 types, right? One is electrical, okay? And the electrical ones have gap junctions in them, all right? Okay, the gap junctions, like in smooth muscle, okay? Interconnected discs in the heart muscle, cardiac muscle, okay? Smooth muscle, gap junctions, and these are ion channels, okay, on the membrane that will let ions pass in and out, right? So when an action potential is happening, which is movement of ions in and out, okay, and these different cells are connected by these gap junctions, interconnected discs, the membrane potential passes faster through a bunch of cells as if it's all one cell, because all the membranes are connected together by these gap junctions. Okay, so that's an electrical synapse. Okay, and it's very important in smooth muscle and cardiac muscle. Okay, and these are gap junctions, and these are interconnected discs. All right, and then the chemical, that's the one that's really the most common. Chemical, it sends a chemical across the gap, which we call the synaptic cleft, right? And then it will attach to a ligand-gated channel. Remember, a ligand-gated channel will open when something attaches to it, okay? Something like acetylcholine is a neurotransmitter that's usually used, and it controls muscles, okay? There are other, neurotransmitters which we'll talk about towards the end of this, like serotonin, dopamine, and so forth, that are communication between neuron to neuron. especially for brain function, right? Okay, so what are the anatomical components of it? Okay, the synaptic terminal, right? Okay, after the synaptic terminal, then there's what? Let me look at synaptic cleft. Okay, after the synaptic cleft is what? The motor end plate, right? Remember what's on the motor end plate? Those ligand-gated channels that receive the neurotransmitter, whether it be acetylcholine and so forth, or it be serotonin, dopamine, whatever the neurotransmitter is. Okay. And also it has enzymes that will break down the neurotransmitter, or like acetylcholinesterase, right? Okay? So activity at the synapse, you could have two things happen at the synapse. What could you do? You could either stimulate, right, the next cell, which is excitatory postsynaptic potential, or you could inhibit, which is an inhibitory postsynaptic potential, okay, an IPSP. So you can do those two things. Know what those things are. EPSP you have to depolarize, to stimulate, and then this one you have to hyperpolarize. And so you can either open chloride channels. Chloride comes into the cell carrying a negative charge, it becomes more negative, it hyperpolarizes, all right? Or you could open potassium channels, because the potassium is inside, it comes out carrying a positive charge, so it remains more negative inside the cell. Okay, so I want you to be able to tell me those two scenarios at the synapse. There are two ways you can stop it, right? You could either break it down enzymatically, that neurotransmitter, so that it doesn't bind to those ligand-gated channels, or you could take it back up, reuptake, back into the, via endocytosis, into the synaptic terminal. You can do that. So sometimes I say, okay, what are the two ways that you can stop a neurotransmitter at the synapse? And then you talk about that. Okay? But then we said there are certain other cells like neuromodulators, right? That can affect the what happens at the synapse, either presynaptically by synapsing with the presynaptic neuron, or postsynaptically by synapsing with the postsynaptic neuron or cell or whatever it is. Okay. So they modulate what happens at the synapse. They can either increase it or decrease it. Okay. See, because this is what happens here. This is, we get our little, this is the presynaptic neuron, okay? And then we have our synapse, and then here we have another one, and this is the cell body. So at the synapse here, you can modulate it from that end, you know, and this end, or you can modulate it from here and there. So this is presynaptic modulation before the synapse, and this is postsynaptic modulation after the synapse. And then you can change what happens in the end result. You can either accentuate it or make it even bigger response, or you can dampen it down. Okay, so that's neuromodulation. So there are certain chemicals that will affect what the activity of the synapse, presynaptically or postsynaptically. Definition, right? Okay, and then clinical examples of synaptic function. Remember, I told you from that big table I showed you many examples of neurotransmitters, and I said I want you to know about acetylcholine, which controls muscles, the myasthenia gravis, you know, how the antibodies will attack those ligand-gated channels for acetylcholine, so that it doesn't matter how much acetylcholine you have, the muscle is not going to respond and you become weak. Okay, so you want to explain that. So that's one of, and then serotonin is another one, and it's involved in depression, because serotonin kind of inhibits unnecessary sort of motor activity in the brain, that is sort of sends you into a depression state. So you have what are called serotonin reuptake inhibitors, okay, and then they will block those sympols that transport the neurotransmitter back into the presynaptic terminal, right? So you block those so that you have more of that neurotransmitter in the cleft, so you have more, you know, you counteract that disease, right? And then I talked about dopamine. I said I want you to talk about dopamine, and dopamine is involved in Parkinson's disease. Dopamine is both inhibitory and excitatory. This one is inhibitory. This one is excitatory. Okay, so I gave you 3 examples. One is inhibitory, one is stimulatory, and the other one is both. The dopamine is both stimulatory and, because I want you to talk about that if I was to ask about these activities of the synaptic clinical functions at the synapse. If you have the clinical, then you know you're talking about these neurotransmitters and their diseases that are related to them. Okay? And then you describe, okay, this neurotransmitter, acetylcholine, is stimulator. Okay, it's involved in myasthenia gravis. It stimulates muscles, right? And then the muscles are no longer being stimulated. So you talk about that serotonin, you talk about that in depression, and then dopamine, Parkinson's disease, shaking. It cuts off the inhibitory function of dopamine, cuts off unnecessary motor activity. Okay, and then so somebody who has Parkinson's doesn't have enough dopamine to cancel that. So it's all right, so synapse. So the chemical synapse activity, we kind of sort of touched a little bit on it. We said you can either excite it by an excitatory postsynaptic potential, or and method of action, mode of action. Okay, how do you stimulate? The only way to stimulate is to get towards threshold, right? And that is depolarization, guys, right? And what does depolarization involve? Which ion?
Sodium.
Doing what? Exactly. So you talk about that. So if I ask about how the how that works, you talk about that, and then you talk about sodium going in. So anything that depolarizes has to open sodium channels. Okay, that's the only way to depolarize, to go up, to become more positive. Okay. So you talk about that. And then IPSP, inhibitory postsynaptic potential. So it will inhibit the next neuron here. Okay, so the definition, it will inhibit, right? It will inhibit inhibitory postsynaptic potential. And then method of action, hyperpolarization. Repolarization is when you have an action potential. Okay, so it's hyperpolarization. And hyperpolarization occurs in 2 ways, right? Which are the 2 ways? The open potassium channels, because there's more potassium inside. That's why it's necessary to remember the conditions at rest. Because if you don't know what's happening when you start, you won't know where you're going. Okay? So you've got to know that at rest, more sodium on the outside, more potassium on the inside. So that you know, if you open a potassium gate, you know what potassium is going to do. Okay? And if you know that potassium is charged with a positive charge, you know what you're going to do to membrane potential, right? Because if you're removing positive charges, it's going to become more negative. Okay? So you really don't have to cram this information in. You can work it out. Okay? Just by knowing the conditions at rest, you can do depolarization, hyperpolarization, repolarization. You can do all that. Okay? It's just a matter of what charge is moving where. That's all. And there are only 2 things you can do here. So it's not difficult, right? You can either depolarize or hyperpolarize. Those are the only 2 ways you can change the membrane. Okay? Okay, so potassium out, right? And then it will become more negative. Because if you want to inhibit something, you move further and further from threshold. Okay, so, and then the other one is chloride. And chloride, you know where it is, right? It follows the sodium, so it's going to be outside. Okay, so if you open chloride gates, what's going to happen? You're going to take a negative charge into the cell, so it's going to become more negative. Okay. You see what I'm saying? There's only 2 ways you can change membrane potential. But you can do it different ways, depending on which ion and which charge. Okay? And where it's coming from. Okay, so it's not that hard. You can work this out. So if I ask about that, I expect you to sort of get all those points. Okay? Okay, so chemical synapse, of course, there are many ways you can sum up these graded potentials, right? So summation happens when you have spatial summation happens when you have 2 or more neurons firing at the same time, simultaneously, right? Each one generates a small gradient potential, and the other one generates another small gradient potential. And before you know it, they add up, and you get threshold, and you have an action potential. Okay?
2 or more firing at the same time?
Same time, yes. I mean, if it's 2 or more firing any other time, is it going to work? It's not going to work. Why? Because we said gradient potentials are conducted in decremental fashion. By the time it goes down and then another one fires, so nothing happens. So if you're going to describe for me spatial summation, you have to say 2 or more neurons firing simultaneously at the same time. That's the only way to add up. See what I'm saying? So this is 2 or more, 2 plus neurons. Same time. Same time is said rather than simultaneous. Sometimes it's too long away. So temporal summation is time. Okay? So it means that you're getting 2 or more action potentials following very closely to each other. So the one action potential comes in, it starts to do whatever, hyperpolarization or depolarization, right? And then before it goes back down, another one comes in immediately after that. So then it will continue to go up. So that's how it sums up. So it's 2 or more action potentials coming close to each other. Okay? Very close to each other. Sort of like high frequency. You have more action potentials for unit time. Remember, that's how you can talk about the size of the stimulus. That's what determines the size of the stimulus anyway. Okay? So you have an action potential comes in, and then another one follows right behind it. Okay? Then you have summation of whatever it's doing. Okay? So now be able to describe those two, and then the way those circuits are arranged, the way the neurons are associated with each other, right? So we got convergent pathways where you have like a whole bunch of neurons converging onto a few, coming together. Converge is to come together, right? Like convene, bring people together, converge. So you've got like 10 or so neurons coming onto 1 or 2, something like that. Okay? 10 neurons to 2. Okay? So they're converging they're sort of all ganging up on this 1 or 2 neurons, converging. Okay? Then divergent, it's like 2 neurons going to 10 neurons. Okay? So one, because it branches, they branch, okay, a lot. So it will go to many neurons. Okay, so this one neuron, when it's stimulated, it has the ability to stimulate a wide part because it will synapse with a whole bunch of neurons, right? Or if you have a lot of stimuli from different places, you can bring it together and be dealt with by one neuron. So that's how the integration function comes into play. Okay? So that you have different messages coming from different parts of the brain and coming onto the same neuron so that you can process a response. You see what I'm saying? No use in having some things happening here, some things happening here, some things happening here. They're kind of connected, but they're not coming together. So you won't have. So that's what happens. Okay? And then oscillating, the neuron, the postsynaptic neuron has those branches we said, those collateral branches that will come back and synapse with the presynaptic neuron. Okay? So that's oscillating. So it kind of goes in circles and it comes back. And this is the other neuron going here. Okay? Branches from there coming to the other one. Oscillating kind of suggests circular. So 4. What is 4, by the way? Endocrine system 1. Okay, so endocrine system 1, we talked about the general sort of functions and and the kind of receptors you have, and the kind of hormones you have. And we kind of concentrated on the water soluble ones in the first part, and then we concentrated on the lipid soluble ones in the second part. Okay, so this is the functions of this are many, right? So you got metabolism, things like cortisol that sort of mobilizes nutrients, thyroid hormones, and so forth. Cortisol from the adrenal cortex, and then you've got T3, T4. All those are involved in metabolism. Remember, T4, jacks up your metabolism by increasing body temperature, mobilizing glucose and things like that from the thyroid. Okay, iron regulation. Okay, some of these hormones will, like for smooth muscle, it will open up calcium channels. and then calcium gets into the smooth muscle and it attaches to camogulin, and you have, so a lot of different functions here. Smooth muscle is an example there. Water balance, okay, and even here you have aldosterone, okay, which deals with sodium, absorption of sodium, okay, and things like that. The sodium, if you absorb more sodium, you have more water in the body and so forth. So that kind of comes to that one. Because it's regulating the ions, and the ions, they always are followed by water. Water goes to where the solids are. Okay, so like in the kidneys, if you are filtering more ions out, like more sodium out, the water will follow it, so you have more dilute urine. Okay, sometimes you retain all the ions in the kidneys, and then the water follows it, so you have more concentrated urine and it's small volume, so you have more blood volume. So it determines how much blood you have, the kidneys do. Okay, by these hormones, like renin influences the blood pressure and which is produced by the kidneys and so forth. Antidiuretic hormone will cause the kidney to retain more ions, and therefore you retain more water. Okay, so antidiuretic hormone, all these things, ADH, aldosterone is also involved, because aldosterone involves retaining more sodium, and so forth and so forth. And atrial natriuretic peptide from the heart muscle, from the right atrium. Okay, when the heart is stretched a lot, it releases atrial natriuretic peptide, which goes to the kidneys and causes the kidneys to release more ions. So water follows it, and you have more dilute ions because you lose water, and then the heart rate and blood volume goes down. Immune system, like the thymus, right? Thymosin, thymopoietin, and so forth, involved in maturation of T cells. Okay, so you talk about all those things. Heart rate, blood pressure, of course, the control of the ions is closely related to blood pressure, because the water follows the ions. You can either lose more water, gain more water to affect heart, blood pressure, blood volume, and then of course heart rate. Okay, and then glucose and other nutrients, regulates that, like insulin, right? And glucagon for glycogen and so forth. So I want you to give those examples when you talk about the functions of this. Reproduction, all those steroid hormones, estrogen, testosterone, and so forth, all those involved in reproduction. So you talk about that. If I ask about the functions of the endocrine system, if you say reproduction and put a full stop, and I'll give you half a point and put a full stop, okay, or a period. Okay, so you need to flesh it out a little bit. Just give a few examples about what it is, and then uterine and breast contraction. The mammary gland, oxytocin. Okay, that's that, causes that. Okay. Also causes ejection of milk. So you talk about that. Okay. So there's many functions of the endocrine system. Like it being the second largest control system, second only from the central nervous system, right? See what I'm saying? And then of course you get those pituitary, hypothalamus, and the pineal body in the head. The rest of the glands are located all over the body, right? Okay, and then you give examples of those, like pancreas, the thymus, the thyroid, all those over here, and then of course the testes, the ovaries for females, all those. Okay, adrenal glands above the kidneys. So examples, and then we talk specifically about. So overview of the. Remember, one of my favorite things is to compare the nervous system and the endocrine system. Okay, so the organs of this we know already, but we already did the organization of the nervous system. So there's the brain and central nervous system, whereas the endocrine is all the glands, right, and tissues that respond to it, that have receptors and cells. For the nervous system, you got neurons and so forth. Okay, for this one, you got cells that have receptors for those hormones. Okay. In the targets, of course, the targets have a particular receptor for that hormone, okay? And then for the endocrine system, and then for the nervous system, it's a synapse. Whichever cell communicates with another cell at the synapse or where they have a synaptic junction, that's how the nervous system influences the other, its targets. Okay, the postsynaptic cell or postsynaptic neuron. And then communication, hormones are in blood, right? They are transported in blood, okay, to other cells. And then, of course, action potential travels along axons for the nervous system, right? Okay, speed. We know the nervous system is like lightning fast, right? Just think of stepping on a tack and how you immediately feel it. Okay, so that's like lightning fast. And duration, you know, is like very short. But for the endocrine system, it's more prolonged, especially for steroid hormones, right? And so forth. And it's slower to act. Okay, and then modulation. We just talked about the nervous system. We said it's the frequency of the action potentials, right? Okay, and then for the endocrine system, how is it modulated? What determines size of stimulus in the endocrine system? How do we know it's a big stimulus or it's a small stimulus in the endocrine system? The what of what? The concentration of the hormone. So if you have a tiny bit of hormone, then you've got a tiny bit of stimulus. If you've got a whole bunch of hormone, big stimulus. Simple, right? More action potentials, which frequency for the nervous system, you know. So frequency for the nervous system, amplitude for the endocrine system. It's size, concentration of hormones. Okay, so hormones, these are chemicals, you know, that travel in blood and are able to affect other tissues that have receptors for them. Okay, and then so we got two kinds of hormones: the ones that are protein and therefore water soluble, okay, and the ones that are lipid and therefore not soluble in water, or lipid soluble hormones. Okay, and these ones have like membranes on the membrane receptors, and these ones have intracellular receptors. Okay, so secretion control, non-hormone substances like glucose will cause the secretion of insulin, right? So that's how hormones, the secretion of hormones is controlled. Okay, or another hormone can cause the release of another hormone, right? Like growth hormone releasing hormone causes the release of growth hormone. Okay, it's things like that. So if I ask about this, how is the secretion of hormones controlled, you talk about that. Or the nervous system can stimulate a gland to release a hormone, right? Like the hypothalamus can send action potential to the pituitary to release a hormone, right? So be able to describe that. Okay, that could be like a 2-point with a bonus. Okay, how you control the secretion of hormones. Okay, so 3 things. Okay. And then water-soluble hormones, you get all these characteristics. They are soluble in water. They're easily transported in blood, right? Because blood is, water itself. And then characteristics, lipid-soluble. They're soluble in lipids, and the way they're transported in blood, they're bound to a protein to make them soluble. All right. So we know about that. And then how do you excrete hormones? So we just talked about control of secretion, and you excrete them by removing them from blood is what we're meaning by excretion here. And you could remove them from blood by attaching to the getting into the tissue, target tissue, right, into the cell. That's how it's removed from blood. And when the hormone reaches its target cell, it will move from blood and then it goes into the cell. So that's one way. Or you can have the kidneys excrete it. Right? The kidneys can excrete hormones, or the liver can do that. Okay, by the digestive system. Okay, so if I ask about hormone excretion, then you talk about that. That's another 3-point question. 2-point with the bonus. Okay, or secretion, how you control it by things like glucose and things like hormones and whatnot and action potential. Okay, very good. Okay, very good. So you get the 2 classes of receptors. The membrane-bound ones are for the water-soluble hormones, because the membrane-bound ones, they span those membrane receptors will span the length, the width of the plasma membrane, and so it will affect what happens inside. If you stimulate that receptor, because it can control the enzyme inside the cell, because part of it sticks into the cell, so it can so it's a transmembrane protein, and it binds to a ligand, which is the hormone. So, method of action of these, membrane-bound receptors, they usually stimulate G proteins, right? The G proteins have the alpha beta subunits, right? Okay, when the receptor attaches to the membrane-bound receptor, it will change shape, and then a G protein can bind, and then it's stimulated, and then you end up having GTP instead of GDP on the alpha subunit. The alpha subunit splits, right, from the beta and gamma subunits, and then it's the alpha subunit that does something. It can either attach to an ion channel, and then you do that, or it can attach, it can activate another enzyme, or it can create a second messenger, like cyclic AMP. Okay, it will like if it stimulates adenylate cyclase, for instance, and then it will convert ATP to cyclic AMP. Cyclic AMP then goes and phosphorylates other proteins and then makes them active. All right. Okay, so that's all that, and then so the intracellular mediators are also called second messengers, like cyclic AMP. Okay, cyclic AMP. It's an intracellular mediator. It's kind of sort of mediates the action of the hormone that is attached to the receptor on the outside and what's happening inside. It's kind of like a second messenger. It checks up, second messenger. All right. So I talked about all this phosphorylation and stuff. Okay. So intracellular receptors, we said there's two: a cytoplasmic receptor for the steroid hormones, the ones that are lipid soluble. They have to always attach to a protein in order to exist in an aqueous environment where there's water. Okay. All right. Or nuclear. Okay. And we said the nuclear ones are a little bit more, polar, and they can kind of sort of exist a little bit in the aqueous environment of the cytoplasm. So they go ahead and directly bind to a nuclear receptor in the nucleus. Okay. But these cytoplasmic ones are usually those very, non-polar lipids that can't really deal with water. So the second part, we're pretty much dealing with the endocrine system too. We're dealing with lipid-soluble hormones and their mode of action. Okay, all right. So we get this binds to lipid-soluble hormones that can cross the membrane, intracellular receptors, right? Because lipids like lipids. So the plasma membrane is lipid, so it can cross no problem. Okay. The only problem is when you're transporting it in blood, where it has to attach to a protein. Okay. All right. So the hormone receptor complex is one that then goes inside the nucleus. Okay. If it is attached to a cytoplasmic receptor, or it will go the hormone by itself into the nucleus, attaches to a nuclear receptor. Then it will bind to those hormone response elements on the DNA, where there's a particular gene in that location that is going to be transcribed by producing messenger RNA, and then messenger RNA comes out, then you translate it into a protein sequence, and then you make a protein. Okay, so that's why these ones have a long lag phase, because you got to do all that production of messenger RNA, and then you do the translation and whatnot. By the time you produce a protein, it's maybe hours after. Okay, so these have a longer lag phase. Okay, so slow acting. All right, what did I do? And then the mechanism of action, of course, I just talked about it, how it comes through the membrane, no problem. It attaches to a cytoplasmic or nuclear receptor, causes photosynthesis at the hormone response element, and then we have effect of protein will be the effect of that hormone. Okay, so mechanism of action, we talk about that. And there's only two kinds. One either attached to the cytoplasmic receptor, or the other attaches to a nuclear receptor. That's it. So there's not, it doesn't differ that much. The rest of it is simple. It's all going into the cell, stimulates a certain gene, and then it's transcribed, translated, protein synthesis. That's all. So you're just describing protein synthesis. We're not really talking about anything very new. Okay, and then we said the posterior pituitary and the anterior pituitary are controlled by the hypothalamus, right? He said the posterior pituitary is controlled by action potential. So it's the neurohypophysis. And the anterior pituitary on the front is stimulated by hormones, is the adenohypophysis. And therefore, that the posterior pituitary has got the tracts, which are the axons. Tracts, remember, axons in the central nervous system are called tracts. Axons in the periphery are called nerves, right? And so those tracts, that's why it's called the hypothalamo-hypophyseal tract. Okay, from the hypothalamus to the hypophysis, which is the pituitary gland. Okay, so that's what it is. Okay, so sometimes I ask about, can you tell me how the posterior pituitary is controlled by the hypothalamus or the anterior pituitary? Okay, So you talk about that. And then the anterior pituitary is hormones. So like growth hormone releasing hormone is released by the hypothalamus, and it causes growth hormone releasing from the pituitary. Okay? And because hormones travel in blood, so there's a connection of blood vessels which are called portal system. So hypothalamus, hypophyseal, portal system. So portal is just another fancy word of blood vessels that carry something from one area to the other. It's a portal. It's a carrier. So there's nothing fancy about that. So and then hormones, hypothalamic hormones, like many of them, growth hormone, releasing hormone, so forth. Growth hormone, inhibiting hormone, releasing all those. And thyroid stimulating hormone, whatnot. Okay? So now we talked about the thyroid, which produces those T3, T4, all right? And then the thyroid, of course, it's got those natural lobes, and it's got the pyramidal lobe, it's got the isthmus that connects them, and therefore, and then it's got the follicles inside that contain thyroglobulin, okay, which is surrounding the T3 and T4, because T3 and T4 are lipid-soluble hormones, okay? So they need to be attached to a protein. So that's why you have those follicles, which are those sort of like lipid bulbs in there, and then they contain the thyroglobulin, which then surrounds those T3 and T4, which are lipid-soluble, right? And then parafollicular cells produce calcitonin. Remember calcitonin that we saw in the bones? We did see that in the bones, so it's nothing new when we talked about how it causes deposition of calcium into the bones. And then, okay, so you need to know the effects of these guys, the thyroid hormones, T3 and T4, about jacking up the glucose level and mobilizing glucose, increasing temperature, increasing heart rate, and things like that, okay, and modulating reproduction and maturation, okay. Those are the effects of that. So sometimes I ask about the effects of these thyroid hormones, and then of course characteristics. The parathyroid, we saw the parathyroid hormone again in the skeletal system, and we know about it already. It was in the exam even. We talked about it. The effects of vitamin D production in the kidney that causes more absorption of calcium in the intestines and so forth, and we get absorption of calcium in the kidneys and whatnot. Okay, and then it can also break down calcium from bone. So gotta know the effects of this, of course. Okay, in the parathyroid hormone gland is at the back of the thyroid gland. Okay, and then this adrenal glands. Okay, it's pretty much like 4 glands in one. Okay, and it's right on top of the kidney. That's called adrenal. Okay, and the adrenal medulla, which is the inner layer, produces epinephrine and norepinephrine. And you know the functions of that, epinephrine and norepinephrine, okay, speeding heart rate, sending glucose and so forth to muscles, and stopping all those sort of visceral activity like to the digestive system and so forth and so forth. So we know about that, fight, flight, okay, and then this zona glomerulosa, the cortex is the outside layer, and it's split into 3. The zona glomerulosa produces mineralocorticoids like aldosterone that deal with minerals, okay, that affect blood content, blood volume. And then zona fasciculata deals with glucocorticoids that produces glucocorticoids like cortisol, which mobilize glucose and conversion of fat and proteins to glucose. Okay, and then zona reticularis produces the gonadocorticoids like androgens, which are the precursors for testosterone and estrogen reproductive hormones. Okay, so know about those layers and what they are producing and then the pancreas, of course. The pancreas has got 2 things. It's got an exocrine function, which we don't care about right now, because we're talking about endocrine, which is the production of insulin by the beta cells and production of glucagon by the alpha cells in the islets of Langerhans, or pancreatic islets. Okay, so know about this endocrine function. Okay, and know where those hormones are produced, which cells produce glucagon, which cells produce insulin. And then the pineal body, we said this one, the function of it is not kind of well known, but it does produce melatonin though, which is involved in the sleep-wake cycles. Okay, so gotta know that, and it kind of sort of inhibits reproductive function a little bit. Okay, all right, but the kind of sort of really common function of it is to regulate sleep-wake cycles. All right, most sleep medication contain melatonin, like sleeping pills. Thymus, this is one that's involved in the immune system, right? It's one that produces thymosins and thymopoietin, which stimulates the maturation of T cells. Okay, T cells are involved in immunity. Okay, so we know about that. Okay, the thymosin and thymosin T cell immunity. Okay, all right. So what else we got here? Other endocrine glands. We talked about it. We said the GIT produces, like the stomach produces gastrin, small intestine produces, secretin, cholecystokinin, and so forth. Okay, and then the kidneys, they produce erythropoietin for red blood cell production. Okay, they also produce renin, which is involved in blood pressure control. Okay, it converts angiotensin, synuclein into angiotensin 1. Okay, so and that deals with blood pressure. And then the placenta, we know about it. It produces first human chorionic gonadotropin, which maintains pregnancy by maintaining the corpus luteum, and then it will also start to produce progesterone and so forth, and estrogen, which maintains the lining of the uterus. Okay, so we know about that. Okay, so I also want you to know about autocrine and there's hormone-like substances. And so autocrine will stimulate same cells locally, though, similar cells. Auto, same cells. Paracrine, different cells. Okay, locally though. Okay, because they don't travel in blood. They're not like hormones, by the way. So they don't go in blood. So they only affect local cells. Okay, these ones will be same cells, and these ones will be different cells. Okay, things like growth factors, they affect many different kinds of cells, so and so forth. All right. So if I ask you to compare hormone-like substances with actual hormones, then you talk about how some of the functions of these hormone-like substances are not really clear. Okay, you talk about how these hormone-like substances only act locally. Okay, they do not go anywhere. Like hormones travel systemically in the blood. Okay, so and then hormones are secreted by discrete glands, like the pancreas, like the thymus, but not these ones. They're secreted by cells, diffuse cells. Okay, so I don't know the differences between hormones and hormone-like substances. Thank you guys, I appreciate it. I'll give you 5, all right? And then, so that's in a nutshell what you need to know. So when you're studying, kind of go through the summary and know those things, because those are things I'll ask about. Okay, thank you guys.